Okay, so we're going to kind of look at this dividing radicals concept. It kind of leans into Algebra 2, and maybe even depending on the state, this is Algebra 1, and some states it might be Algebra 2, but these are some tricky concepts. So, but let's kind of look at number 1 and kind of think about it. So there's we could put it all underneath the same radical if we look at it this way, and by doing that we can kind of see that we end up with the square root of 1 over 2. Now if you factored it, we would get the same thing. So I'm going to factor just to show you that I would have the square root of 4 over the square root of 3 for the numerator, right? And then here I pulled that a perfect square. I'm going to pull out the square root of 4, but then I'm going to have the square root of 6, right? And now these two, of course, anything in the numerator and the denominator just cancel out because, well, anything in the numerator and the denominator, and I can already see I'm kind of getting close to halfway, right? And so let's factor this square root of 6 just to see what happens. I can factor to the square root of 3 times the square root of 2, right? And what do I end up with? Well, again, anything in the numerator and denominator just cancel out because anything divided by itself is 1. And so I'm left with this 1 over the square root of 2. And that's really what this is, because if I go back, I would end up with the square root of 1 over the square root of 2, and the square root of 1 we know is just 1, right? Because we know our perfect squares. This is kind of getting a little lost here. Let me just kind of fix that. So this becomes 1 over the square root of 2. But something that you have to realize is that when we are dividing radicals, there's something called rationalizing a denominator, meaning we don't really want to leave irrational numbers, and that's what a non-perfect square value is. So like 6 is not a perfect square. The square root of 6 is not going to get us any number that's not going to it's going to terminate. It's not going to repeat. It's not going to terminate. So this number goes on infinitely. So we don't like to divide by numbers that don't terminate or repeat just because it's very messy. So how can we do it? Well, we can kind of go back to some principles that you learned a long time ago, back in like 6th grade, and you can multiply it by the value of 1, right? Anything over itself is 1. And what is useful about that is if I kind of just look at this, I can see right away that I'm multiplying these two in the denominator, and so that would give me 1 times the square root of 2 in the top, which is just the square root of 2, and then the square root of 2 times the square root of 2 on the bottom, which is the square root of 4. So I end up with the square root of 2 over 2. And this, in fact, is the simplest form of this problem. So it's the simplest way to rationalize the denominator. So here we can do this real fast. We have this square root in the symbol right here, so we can just multiply it by the square root of 7 over the square root of 7 real fast when we see the idea. And we don't need a perfect square for this, but we can now multiply, and we get 4 square roots of 7. We can multiply these two over the square root of 49. And the point behind it is that when I multiply two numbers to get the square root, the rational value of a perfect square is just going to be to find one of its factors if it's non-terminating and non-repeating. So this is a perfect square because this terminates. This number does not have any decimals. It could have decimals, but those decimals would have to terminate. So this would be our simplest form of that problem. So here we get into kind of this looks a little more tricky than these problems, and this really kind of leans into Algebra 2 a little bit. So I can't just simplify this. I have to go back to another principle, which I haven't covered in any videos yet, but I'll be releasing some, and it's the difference of two squares. So the way to do this is to multiply, and I did it on these two, I just didn't call it that, but I multiply by something called the conjugate. So the conjugate, yeah, this is not English class though, or Spanish or any other language class where you are conjugating verbs. But what we are doing is we are going to multiply it by a number, which is the value of 1, just like we multiplied over here by square root of 2 over square root of 2, and we multiply the square root of 7 over the square root of 7. We are going to multiply by a number that is, in fact, itself, right? So this becomes 1. But why did I use, say, this number? And this comes back to a principle that you would have learned back in Algebra 1 if you got through it, but if you're in the middle of Algebra 1 right now, you probably haven't learned this yet. So let's just kind of look at this. If I think about the numerator, I'm just multiplying across, right? I distribute, so I would end up with, in my numerator, I would have 2 times 1 minus the square root of 5. And in my denominator, I have this 1 plus the square root of 5 times 1 minus the square root of 5. Now, somehow this is a little tricky, but let's just multiply it out so we get the idea. So I'm going to have 2 times 1 is obviously 2, and then there's an imaginary 1 in front of any radical when there's no number, so this is going to be 2 square roots of 5. And then on the denominator, so this is where it gets a little tricky. I have to multiply 1 times 1, right? I have to distribute. I'm going to distribute. And this is an old method, and I really wouldn't do this method other than in this moment. There's a cleaner method, but this one's okay. And so because it doesn't always give us clarity as to what's happening, but this method works. And this is kind of, I think they call it FOIL. The multiply, it's really just double distribution. So I'm going to distribute this to both of these, and I'm going to distribute this number to both of those as well. So when I distribute the square root of 5 to this, I get plus the square root of 5, right? And then when I distribute the 5 to over here, I get minus the square root of 25. And why is that useful? Because what we talked about above is that if we have the coefficients, or in the last video, if we have coefficients the same, we can just add them. So negative 1 plus 1 is 0. So these, in fact, just cancel out. So my numerator is 2 minus 2 times the square root of 5 over 1, and the square root of 25 is 5. And so we can simplify this to 2 minus 2 square roots of 5 over negative 4. And so, okay, we could take this just a little bit further if we really, really want to. I'll just kind of guide you through that. I could say, and I'm going to take this negative sign and just put it in front of the fraction for a second. Yeah, well, actually, I won't do that just yet so I don't confuse anyone. But I'm going to say 2. I'm going to remind you that this negative 4 is the denominator of both of these. So I'm going to put this over here, and then I'm going to put it over here, right? So I have this negative 4 underneath both of these. So if I simplify this first one, this just becomes negative 1/2 plus, well, plus positive 1/2 square roots of 5. Okay, and this is our simplest form. I can't really go any further, but why is this positive? Because a negative divided by negative is positive. Now, some people will just kind of want to write this in a different way, but this is probably useful enough to understand, and you probably can work that out, which I don't want this video to get too long, so I'm going to work this one out, just kind of showing you the procedure where I'm just multiplying by the conjugate, right? And the point behind the conjugate is it is the difference of two squares, and you'll see that in higher math. But this gets very tricky very quickly as you get into kind of these bigger situations. But the top, I'm going to have 6, and then I'm going to have minus 2 times the square root of 2. And then I'm going to have the square root of 3, right? So I'm going to minus 3 times the square root of 3. And then I'm going to have this plus the square root of 6. So all these things are actually different. So I can't actually combine any of those in the numerator. And then in the denominator, I would have 3 times 3, which is 9. Again, that's a perfect square. And then 3 times this over here is minus 3 square roots of 2. And the square root of 2 times 3 is plus 3 square roots of 2. And then the square root of 2 times the negative, which is minus the square root of 4. Now, again, this is the reason why we do this is these are opposite values, so they just cancel out. They equal 0. And then this is just 9 minus 2, which is 7. And then our numerator, we would have 6 minus 2 square roots of 2 minus 3 square roots of 3 plus the square root of 6. And really, there's not much else we can do with this problem in terms of simplifying. This looks kind of complicated and whatnot. You could find equivalents of it, and yeah, maybe I could factor a little bit or do a couple other things, but this looks about as simplified as you're going to get it, and it looks awkward, but that is the procedure. So.